Hello everyone, welcome back again for the successive class on numericals on optical fiber. In this session we are going to solve some of the assignment questions that were given in assignment 3A, and this class will involve the solving of all those problems and also the explanation. The prerequisite for all these problems, the mathematical relation, has already been uh, given out as a video lecture in the prerequisite part. You can refer to it. Well, let's get back to this problem. The very first question in the assignment 3A was this over here. Calculate theta 1, theta 2, theta 3 dash and theta phi in the below figure of optical fiber. Also find the critical angle theta c for the given setup. For what value range of theta 1 and theta 2 will the total internal reflection be possible? Though it looks very complex question, it is very simple, which involves the very basic concepts of total internal reflection, critical angle, numerical aperture, and also the basic geometrical arguments such as alternate angle, vertically opposite angle, corresponding angle, and all those. Now, don't confuse yourself with the symbols that you are using in your module and the symbols given over here, because symbols are always arbitrary. That is, n1 n2 was always with respect to core and cladding, but here n1 is the refractive index of the external medium and n1 becomes, which is the core's refractive index, and n4 here is your cladding's refractive index. So systematically get used to a new symbol and correspondingly affiliate with the corresponding symbols that you are using in your textbook or your methodology. So for the purpose of that, I am giving you clarity while solving it, so get used to that. Okay. Now as soon as the problem is given, like I said, write down the given data. The given data over here is n1 is 1. n1 is the refractive index of the surrounding media, that is air basically. According to this, it is n1, and according to our methodology, our symbols that we follow is n0. Okay, this is your n1, and in our case we follow n0, so I have written in the bracket. n2 over here is the refractive index of the core, which is 1.48, and in our methodology we call it as n1. And n4 over here is a cladding's refractive index 1.44, which is of course lesser than the core's refractive index, and in our case we call it as n2. Okay. These are the given data. Now what is to be found? It has to be seen that acceptance angle, that is theta 1, has to be calculated, that is theta 0 in our case, and the rest of them theta 2, theta 3, theta 3 dash, theta phi, and theta c, which is a critical angle, have to be found out. Once you have the clear picture of theta 1 and theta 3, the rest of them are pretty much easy because they are geometrical arguments. Let's see how this is solved. The very basic mathematical relation that you are going to use is theta 0 is equal to sine inverse of root of n1 square minus n2 square by n0, which we have been saying throughout the lecture. Now if you put this value n1, n2 and n0, which is equivalent to n1, n2 and n4, you directly get the acceptance angle. Okay, so you substitute the values, 1.48 square minus 1.40 square by 1, you get 28.68, roughly 28 or 29 degrees approximately as your acceptance angle. Well, this is a acceptance angle for the given setup, but he has also asked what is the critical angle and the real values of theta 2, theta 3 and theta 3 dash when there is a possibility of complete total internal reflection to happen. For that, you have to go a little bit ahead and think about theta c, which is critical angle. Okay. So critical angle is defined as, through your Snells Law equation, theta c is equal to sine inverse of n2 by n1, which is basically saying that there is a spot where the whole, that is this particular from this point to this interface between the core and cladding, and this ray over here is just grazing the surface, making 90-degree, and that makes and gets this particular value. Okay, using Snell's law, you can see that here sine of theta 2, okay, basically becomes sine of 90, and that is how you obtain this relation when you go back and look into the theory. So hence, any angle, that is this angle theta 3, greater than the critical angle, can only make sure that light gets back into the system and behave and move in a particular waveguide fashion. So you have to calculate that critical angle. This is a criteria or the limit that you will calculate for total internal reflection to happen. So substitute the values and you get this critical angle. So 76.65 degree is the angle. By substitution you get this value. Roughly 77 degrees is the angle at which, okay, if this angle, that is theta 3, which is theta 3 over here, is more than this angle, then only light completely reflects back into the system. Thereby you have total internal reflection. Okay, so theta 3 angle over here should be more than 77 degree or 76.65 to be precise for TIR to happen. Okay, so some of the part is solved already. Now let's go ahead and solve the rest of the parts, that is theta 3 dash, theta 2, theta 5, all these values let us calculate. You see here theta 2, okay, which says that angle of incidence is equal to angle of refraction. But to have a perfect value through your critical value and all those, it is easy to use this theta 3 dash and try to understand what is the value. So theta 2, from this triangle over here, if you know theta 3, you can easily know theta 2 because it's a geometrical argument again. So you have this and you can calculate. So all these three angles together forms 180. So you can get theta 2. As well, if you know theta 1, you can calculate theta 2. But if you want to have the value of theta 3 dash, it is pretty simple. Okay, you have a ray that is standing on this line. So 90 minus theta 3 dash or theta 3 will fetch you theta 3 dash. So theta 2 and theta 3 dash are almost same. It can be either got from this triangle, theta 2 can be got from this triangle, or if you know theta 3 dash, or if it is theta 1 is known. All the three arguments are same. But in this case, theta 2 is equal to theta 3 dash is a geometrical argument. It says alternate angles. This Z type or Z shape says that this angle and this angle are equal. You might have already learned all these in the geometrical arguments in your lower standards, where you have seen that there are two parallel lines and there is a ray that is standing on it. Then you have these alternate angles. So theta 3 dash and theta 2 will be equal. Call it as an alternate angle. It's a geometrical argument. So basically theta 3 dash can be got by 90 minus theta 3, that is this over here. So this is your 90. 90 minus theta 3 will fetch you theta 3 dash. Why we use this is because everything is revolving around theta 3, which is basically following the principle of total internal reflection, which is critical angle. The angle which is greater than the critical angle can only get back the ray into the system following a total internal reflection. Okay. Now this forms the basis for the calculating the so-called your ranges for theta 1 and theta 2. So finally theta 3 and theta 5 are alternate angles for parallel line. Okay. Therefore the two angles are also equal. Again this argument also is same. So you have a Z shape over here. Okay. So basically this angle as well as this angle over here, it's same. So you found out theta 1, theta 2, theta 3 dash and theta 5 in general. Okay. Now if you want to have the exact value of it, you go further and calculate by using Snell's law. Snell's law at the entrance will be given by n1 sin theta 1 is equal to n2 sin theta 2. N1 is over here, okay, which is our notion of N0. Remember, it's not the N1 over inside, but it is N1 is the external agency refractive index, whether air or water or any liquid or anything. N2 is the system at the center, that is nothing but your core, okay, not the cladding but core, So this is your Snell's law according to this. As soon as the light enters into the system, the Snell's law is given by this. Now, geometrical argument and all those will fetch you this particular condition, that is what is the angle of so-called refraction. Angle of refraction is pretty much understood by using your previous equation, that is what angle you calculated, that is your 76.65, which means that this angle also can be calculated, which is your so-called 13.4 degree. Now this is your 13.4 degree. Okay, by the argument of the critical angle, so we say that theta 2 should be less than 13.4. It should be less than, because it is, this should be greater than, so this should be less than, this should be less than. Okay, if it is more, if it is greater, this becomes less, so that this grazes the surface and gets back into the system. So this should be less and less for total internal reflection to happen. So if theta 2 is less than 13.4, then only total internal reflection can happen. Then you can put in the argument of inequality and say theta 2 is less than sine of 13.4 degree, so that we are keeping all these in between 0 to 90. Otherwise inequality might not hold. That is the whole argument. Okay. So by using Snell's law, you further calculate the relation or the limit of theta 1. Try to understand theta 1 and theta 2, right? For what values of theta 1 and theta 2 will total internal reflection be possible? Go further and calculate. So you put sine theta 1 is equal to n2 by n1 sine theta 2. This is just a simple Snell's law that you are putting, and you put the inequality. Though there is a equal, don't get confused. We are trying to solve the inequality problem. Okay, is lesser than n2 by n1 sine of 13.4. Okay, so theta 1, you put in the values, and finally you will see that theta 1 is less than sine inverse of 1.48 by 1, that is light entering from the external end into the system. So what would be your limit for your acceptance angle? So that is C, and finally we see that theta 1 should be less than 20, not 28 degree. Remember, 28 degree is for given system. If you see that the 28 degree is for given setup, but 20 degree or less than the values for theta 1, that is your acceptance angle, should be less than 20 degree. Okay. Now we have the complete argument. We know theta 1. Once we know theta 1, we know the limits. Theta 1 should be less than 20, and theta 2 will be the same, because angle of incidence is equal to angle of refraction. So we know what is the value of theta 3. Theta 3 should be greater than 76.65 degrees, and same thing applies for theta 3 dash. Same thing applies for theta 5 with respect to theta 3, because they are alternate angles. So this completes this particular problem. This is just a limiting value. This is more a fundamental problem setting the limits for the total internal reflection to happen. Okay. This problem, though kind of a twisting and very deep level problem, and very confusing probably for some people, you have to understand that these symbols should be translated according to the given language. Don't stick on to NO, N0, N1, N2 and all those. They might twist this and ask you. Only thing you have to understand is that this theta 3 over here, okay, should be greater than your critical angle. So the theta 2 should be lesser to some value. What you see, the value what you found is 20 degrees. Theta 1 and theta 2 should be less than 20 degrees. Then only light will get back into the system. If it is exactly equal to 76.6 degrees, that is theta 3, then it will just simply grace, creating your limit of so-called your refraction, total internal reflection. Okay, setting the critical limit. All right, let's get into the other part of it. So for total internal reflection to occur, theta 3 must be greater than critical angle. Therefore, theta 3 is equal to, by geometrical argument, 90 minus theta 2, that is this over here. 90 minus theta 2 is greater than, that is your theta c. So 90 minus critical angle should be greater than theta 2, and hence theta 2 should be lesser than 13.35. Now we are calculating theta 2. Okay, theta 2 should be lesser than 13.35. Okay, the angle of refraction at entrance must be less than 13.4 if total internal reflection to occur at the upper edge of the fiber. So now you have the limit. The theta 1 should be lesser than 20 degree for this to happen, and theta 2 should be lesser than 13.35 degree. Okay, all right. Now let's move on to the next problem. The next problem is an optical fiber has a core material with refractive index 1.55 and its cladding material has a refractive index of 1.5. The light is launched into it through organic liquid. The numerical aperture of fiber under such condition is 0.26016. Find the standard organic compound solution used here based on the data given. Also calculate the acceptance angle when the light is shot from the water in optical fiber. Given the refractive index of water is 1.33. We also given the refractive index data table here. You can visit that and do it. Now this is a little bit interesting problem. Okay. So here the optical fiber's core refractive index is given 1.55. Claddings is given. When light is launched into this optical fiber through any organic liquid, he's saying organic liquid meaning it can be toluene, okay, benzene, or any kind of organic liquids, any chemical compounds, okay, which is showing some kind of refractive index behavior. That is, light traveling into this, the light components getting slow down, or okay, or light components is deviating. All these behaviors are shown in this liquids. So you have to find that liquid based on the condition of numerical aperture. Remember, the refractive indices of core and cladding won't change irrespective of liquid or anything. Only the angle of so-called numerical aperture as well as the acceptance angle will only change, which is dependent on the refractive index of the material that you are using, that is your liquid that you are using or a medium. So this is two-folded, the problem. The very first case is you have to find the type of organic compound. To find the type of organic compound, you have to know the refractive index of that organic compound. The second one is you have to calculate the acceptance angle for the same optical fiber when it is kept in water. Okay. So for this, let's write down the given data. The given data is, use your common notion, that is N1 is your refractive index of core 1.55, which is of course greater than N2, which is 1.5. The numerical aperture of this so-called optical fiber when kept in organic liquid, this is what I'm saying. Okay, numerical aperture changes with respect to your system, because you have that N0 quantity, that is you have to remember. Okay, is equal to 0.26016. Why this precision? Because we require this precision just to make sure that no other liquid matches with this value. Okay, so just be careful with that. All right, to find N0, N0 is the medium's refractive index. Generally we call it as air, where N0 is equal to 1. Water, it is 1.33. Now this organic liquid we have to find. To find what is the type of organic liquid, you have to know the refractive index of this organic liquid. And finally, you find what is theta naught, that is acceptance angle when kept in water. Write down the given values and write down the values that have to be found, and then go ahead. You can write the sketch diagram. You have the optical fiber. N1 is the refractive index of core, N2 is the cladding refractive index, N1 is greater than N2, that is the condition. N0 is the system's refractive index, that is nothing but your external system. Okay, and theta naught is your acceptance angle. Now use the equation theta naught, which is quite well known now by now, sine inverse of root of n1 square minus n2 square by n0. So this is the quantity that is required in the very first case. So let's solve the first case. The problem is split into two cases. One is to find the refractive index of organic liquid that you are keeping so that your numerical aperture is 0.26016, and also to find the organic liquid. We compare the N0 that is calculated, you find it and use the experimental values and calculate. And the second one is when the same optical fiber is kept in the system where N0 is 1.33 for water. So what is the acceptance angle? So numerical aperture is just sine of theta naught. Okay, just inverse functions. Remember. Okay, so this formula or mathematical relation is quite simple. Theta naught is your acceptance angle. Sine of theta naught will give you your numerical aperture. Numerical aperture is just a number. Okay. Now, why we converted it to numerical aperture? Because numerical aperture for the organic liquid, okay, in this scenario is given already. So numerical aperture is equal to sine of theta naught is equal to root of n1 square minus n2 square by n0. In this case, n1 is known, n2 is known. N naught have to be found out, and Na, which is sine of theta naught, is already given. So in the first case where you have to find the refractive index of the organic liquid, so use this equation. Na, that is numerical aperture in the organic liquid, is equal to numerical aperture of the optical fiber when kept in organic liquid is equal to root of n1 square minus n2 square by n naught. Put in the values, or you can already shift n naught that have to be found out and take this. So by substituting the values, you see here n naught 0.26016, which is numerical aperture of the optical fiber in the organic liquid. When it is kept, you have this is equal to root of 1.55 square minus 1.50 square whole root divided by n naught. You shift this parameter which have to be calculated. N naught is equal to root of this divided by 0.26016, and finally you will calculate n naught is equal to 1.501. So this is the refractive index of the surrounding medium or the organic liquid. Now we have the value, but we don't know what is the refractive index of it. So it will little bit twist in this problem. Why this problem was given? So that you can have some extensive legwork on this on Wikipedia or any sources external, and you can have some fascination towards the problem. Okay? Instead of using the same monotonous way of doing the problem, this has a little bit twist and turn so that you can find the data. Okay, so you have some enthusiasm towards learning this particular problem in a different manner. So once you found out n naught, okay, compare this value. We have found out that is n naught is 1.501, which is quite different from water. Water is n naught is equal to 1.33, which is already given here. Okay, which will be calculating shortly. N naught for air is 1, but for liquid that we are using here is 1.501. To find out what liquid, you compare this value in Wikipedia or any sources. The simple source is given refractiveindex.info. Click on it and go there and find it out. And once you find this matches exactly, and we find the corresponding compound which is having n naught value of 1.501 is benzene. Okay, so you found out that it's a benzene, that liquid is there where optical fiber has immersed, and when light travels inside this benzene with refractive index 1.501, then the numerical aperture, okay, is such a way the total internal reflection is happening is 0.26016. So you are calculating, okay, or you are knowing benzene through just this number. This number is telling, okay, this is your refractive index of your so-called liquid that corresponds to benzene. So this first part of the problem is solved. That is, what is the refractive index of your external medium or the liquid, and what is the type of liquid. You have answered both. N naught is 1.501 and benzene is the liquid that you are using. The second part, when the same optical fiber is kept inside a liquid which has a refractive index 1.33, which is already given, water. So I don't want numerical aperture, I want acceptance angle, which is both same, because we have seen both same in the sense they are very equivalent to each other. Sine of theta naught will give you numerical aperture, sine inverse of numerical aperture will give you theta naught. Okay, you can calculate easily. But we want theta naught. Okay, n1 is known. Okay, refractive index of the core, n2 is the refractive index of the cladding, n naught is the refractive index of the surrounding medium. So you put in all the values, it's a direct problem. So theta naught is equal to sine inverse of, substitute the values, we have water's refractive index, n naught, n1 and n2, we substitute and we get the value. Theta naught is 19.79 degrees. Okay. The previous problem we were solving, what is the limit that you are using, okay, so that total internal reflection can happen. Theta naught is 19.79. So sorry, solved. So summarize it. Summary is of this whole problem is that we have found out the refractive index of that liquid, which creates a numerical aperture of 0.26016 is 1.501, and the organic liquid is benzene. You have found out using the database, okay, or Wikipedia or any external source. And the acceptance angle when the same optical fiber is kept inside water is 19.8 degrees. So this completes the solution of this problem. The next problem that we have seen is here. The angle of acceptance of an optical fiber is 28.75 degrees when kept in air. That is, you take your optical fiber, you keep in air, and whatever acceptance angle theta naught that you are seeing is 28.75 degree. Okay. Find the angle of acceptance when it is kept in a medium of refractive index 1.361. Now he is changing the refractive index of the medium. You know, a refractive index of the medium symbol is N naught. Okay, N naught is 1.36. So you have to find. There is no N1 given, that is, there is no coarse refractive index given, cladding's refractive index, there is no data from the optical fiber. He is just saying N0 is given and then your optical fibers theta naught is given, you calculate. Write down the problem. What are the given data and you will understand. The given data is theta naught when it is in air is given 28.75 degree for an optical fiber. N0 is given, which is ethanol, C2H5OH is ethanol, okay, ethane alcohol or ethyl alcohol. So when you keep the optical fiber inside this, what is the angle of acceptance is what has to be found out. So you have to find theta naught when the whole optical fiber is kept inside ethanol. So though it looks simple, it is not simple unless and until you have the equation. The equation is general one which you already have studied. So first have the proper sketch. N0 is the medium. It can be air and it can be liquid or any kind of medium. You have optical fiber again. N1 is the refractive index of the core. N2 is the cladding refractive index. N1 is greater than N2. Theta naught is the acceptance angle. When you keep in such pattern, when light enters, so when it has to go through this total internal reflection and all those critical angle and all those things, you have to find when N0 is air, okay, you have the acceptance angle as 28.75 degree. But the same thing is kept inside a medium's refractive index of 1.36. What is the theta naught? That is the question. It is already given. It is ethanol. Basically, it is ethanol. When you keep the refractive, the optical fiber inside this ethanol, so what is this theta naught? This is a relation that is need to be understood. Okay, the basic equation is theta naught is equal to sine inverse of root of n1 square minus n2 square by n naught. Same equation. Okay, n1 is a refractive index of core, cladding refractive index of the surrounding medium. In this case, it is air and ethanol, and theta naught had to be found out. For air, the first case where he is given theta naught corresponds to 28.75 degrees in when the optical fiber is kept in air. Okay, you directly fill it out. Okay, theta naught in air is equal to sine inverse of root of n1 square minus n2 square. Remember, n1 and n2 is not given. It's a special case. So put in the values. So by substituting the values of theta naught, okay, you have 28.75 degree is equal to sine inverse of root of n1 square minus n2 square. Well, you find a dead end here. You have a couple of variables. If you have only one variable, it is easy to solve. When you have two variables unknown, which are unknown, you don't know. So just see here, 28.75 degrees is equal to sine inverse of root of n1 square minus n2 square. Take the inverse function and just find the value of root of n1 square minus n2 square. Okay, sine of 28.75 degree, that is you are taking inverse function on both of them and sine inverse and sine goes off. Sine of 28.75 is equal to root of n1 square minus n2 square. So finally you find this value root of n1 square minus n2 square together cumulatively gives out 0.48 for your air. Not an issue because n1 square and n2 square they won't change at all because it's an intrinsic property of the optical fiber, remember. Okay, so n1 square minus n2 square you have the value. Okay, there is no n0. N0 is more or less 1, which doesn't make any change. If it was different medium, you can't compare, remember. Okay, now if there was a different medium and then you start the point this, then you would land in trouble. But here it starts with the very pristine starting point, that is very basic level, that is your air. So 0.48 is the value. Substitute this value into that and you get the value of theta naught, that is your acceptance angle of the optical fiber when kept in ethanol. So now you know the value of n1 square minus n2 square root, so you have the value. Now for ethanol, when you keep the optical fiber in the ethanol which has a refractive index 1.361, the equation for theta naught is equal to sine inverse of root of n1 square minus n2 square by 1.361. Okay, Now you know the value of sine n1 square minus n2 square root. Okay, so you put the value, you already know it. Okay, because you have divided by 1, so it doesn't make any change. You can put the value safely. When you put the value, substitute the value of n1 square minus n2 square root, we get theta naught ethanol is equal to sine inverse of 0.481 divided by 1.361, okay, which is equal to 20.7 degrees. So you have the value already. So this is kind of a twisted problem which misleads in many manner, but you have to focus and you get it. Okay. Now you go to the next problem in the assignment. The core diameter of multi-mode step index fiber is 78 micrometer. The thickness of the optical fiber is given, which is also said that it is a multi-mode step index fiber. Okay, which means that the n number of waves can pass through it, so there can be a number of modes of propagation that can happen. The difference in refractive index is 0.025. Again, little bit twist. Okay. The core refractive index, what is the 0.025? It is the difference between the refractive index. There are only two refractive index inside the optical fiber, N1 and N2. The difference is 0.025. The core refractive index is 1.57. Determine the number of guided modes when the operating wavelength is 0.625 micrometer. The coarse refractive index is given. Only one parameter is given in the case of N1 and N2. N1 is given, N2 is not given, but it says there's a difference is given. And you have to now determine the number of modes. That is, you have to find the number of modes. How many modes can this particular optical fiber can accommodate when the light of wavelength 625 nanometer or 0.625 micrometer is used. Some red color probably. You had already done experiments in your laser diffraction experiment. 625 corresponds to more or less red or orange color laser. Okay. Alright, the given data N1 refractive index of the core is 1.57, but N2 is not given. But N1 minus N2 is given. How you know it is N1 minus N2, not N2 minus N1? It's quite obvious because N1 is always greater than N2 in the case of optical fiber, so that argument stands. So easily you can calculate N2. Okay, N2 will always be less than this, so that is very important. Is equal to 0.025. The thickness, that is D, is given. Converted to SI unit, 78 micrometer. Micro is not a unit, it is just a prefix. Okay, it's just an exponent that you are using. 10 power minus 6, part of a million of meter. 78 into 10 power minus 6 meter. Lambda is 0.625 micrometer, 625 nanometer, but in terms of SI unit, 0.625 into 10 power minus 6 meter. You have the given data. What are the things you are supposed to find out? You have to find out number of modes. Number of modes and V number are related. So V square by 2 approximately is number of modes. So let's go ahead and calculate the V number. Use the V number formula. V is equal to pi times D divided by lambda root of N1 square minus N2 square by N0. Here N0 is not known, right? N1 is known, N2 is not known, rest of them is known, D and lambda is known. So now what you do is that put the value of N2. For knowing the N2, you have to find N2 using the difference between N1 and N2, and condition is N1 is greater than N2, which implies N2 is equal to 1.545. I don't have to repeat this again. In optical fiber, the refractive index of core is greater than refractive index of the cladding, and the condition given is N1 minus N2 is 0.025. Obviously, N2 is less than the N1, so basically 1.545 is your cladding's refractive index. Once you have N1, once you have N2, and the condition here is that N1 is N0 is air. Okay, whenever there is no material or the refractive index of the medium is not given, assume it to be air. Okay, so substituting the value of N1, N2, D, lambda, and N0 is equal to 1 for air. Whenever there is no refractive index of surrounding medium given, keep it as 1, which is air. We get V is equal to, substitute the values, 3.1416 into 10 into 78 into 10 power minus 6, which is the thickness of the material, that is diameter as well. 0.625 into 10 power minus 6, they both cancel out. Okay, root of 1.57 square minus 1.542 square, which is the refractive index of the core at the cladding, and N0 is the surrounding refractive index of the medium. we get 109.41 as your V number. Well, this is nonsensical. It doesn't make any sense, this V number. It doesn't have any physical interpretation. To have the physical interpretation, we have the approximation which says that for multi-mode step index fiber, apart from single mode step index fiber, the number of modes that can be accommodated will be square of this divided by 2. So number of modes will be approximately equal to V square by 2. So number of modes now approximately equal to V square by 2 is equal to 109.41 square. There is a small mistake over here. It has to be divided by 2. So we take it out and make it as, so roughly it will be around 11,971 divided by 2. So which will be 5,985 modes, or roughly around 5,986 modes. Okay, there's a small correction over here. V square has been done, but V square by 2 has to be done. So this will be 11,971 divided by 2, which is 5,986 modes, or number of modes that is accommodated in the optical fiber. Okay, all right. This completes this particular problem. Summarize it, and then let's go ahead. Last problem that we are dealing is pertaining to the attenuation problem. An optical fiber has attenuation, which is the intrinsic property of optical fiber. It doesn't change with respect to length or anything. Attenuation remains same. Okay, remember. Now attenuation is a property. Of course, it depends on the how much power goes out depends on this attenuation property. So attenuation in an optical fiber is 4.3 dB per kilometer. Again, it's a relative unit. Okay. For 1 kilometer, it is showing 4.3 dB. What fraction of its initial intensity remains after 2/4 kilometer and 3 times the 2/4 kilometer, or 3 times the distance of the same? Little bit straightforward. At the same time, there is a little bit of twist in the problem. For that, we can write down what are the given data. The given data is alpha is given. Alpha is known. It is a coefficient of attenuation, or attenuation coefficient, which is 4.3 dB per kilometer. Okay. Now this is the intrinsic property of the optical fiber. You have to find what is the initial intensity, that is input amount, that is your how much amount of input power that you put in remains after 2/4 kilometer and 3 times 2/4 kilometer. That is nothing but 6/3 kilometer, 6/3 or 6 kilometers and 3/4 of a kilometer. So we'll write down what are the things to be found out. You have to find a P out by P input ratio after 2/4 kilometer to 1/4 kilometer. Okay, and P output by P input ratio after 6 times 3 by 4th kilometer. That is 3 times this will be 6 3 by 4 kilometer. Okay, convert all these into proper decimals. Convert this into fraction value into decimal, then you will land up. So quarter of a kilometer is 0.25. Okay, remember that. So that's nothing but 250 meter, and 0.25 meter. Okay, 0.25 kilometer, and 3/4 is 0.750 kilometer. So it will be 2.25 kilometer and 6.75 kilometer. That you have to find out. So this ratio, that is how much amount of output power what you get. Okay, with respect to input, you don't know P input, P output and all. Okay, we want to calculate the ratio. We want to calculate the ratio for this much amount of length and this much amount of length of optical fiber. That is the distance at which these are traveling. All right, use the equation. Alpha is equal to minus 10 by L, which is the distance. Okay, log to base 10 P output by P input dB per kilometer. Now we know that P input, P output is not given. Remember. Okay, alpha is given. L is given, but in a different sense. L, the whole problem revolves around L. Remember, for 2/4 2.25 kilometer, what is the P out by P input ratio, and for 6.75 kilometer, what is P out by P input. That is you are supposed to find out. But if you want to find out P out by P input, it is already stuck inside this log function. You have to remove out of this log function. For doing that, you have to take the inverse of this log to base 10 function. What is the inverse of log to base 10? Okay, so we have to find P output by P input 2/4 kilometer and P output of P input 6/3/4 kilometer. Imagine there is a power station where you have a signal that is generated that is traveling from one point to another point where that is a receiver station. There is a length of 2/4 kilometer. Okay, when you send a signal from here, that is the input power P input. Okay, so how much remains after 2/4 kilometer? Because there is always losses in the optical fiber. So how much it remains? And then further, after 3 times this length, how much remains? That is how much is the output of power that is to be calculated. Alright. Now to calculate P output by P input from the alpha, you see the equation over here which is in the unit dB per kilometer. You have to take the inverse function on both sides because you have to get rid of log to the base 10. On simplification, to extract P output by P input, we get minus alpha into L divided by 10. Okay, so you are just simplifying, you are not taking inverse function yet. Okay, L is multiplied here, minus 10 is divided, you just simplify. Okay, make sure that you have only P output by P input into so-called your log function. Okay, now you have the P output by P input, but your P output by P input is inside the log. This ratio is inside the log. You have to remove log to base 10. Remember, when you have to get rid of sine, you have to multiply it with sine inverse. When you have logarithmic to base e, you have to multiply it with exponential e. That is, you have to take exponential function. If you want to get rid of log to base 10, you have to take so-called 10 to the power x. That is log to the base 10. So inverse of log to the base 10 is 10 power x. You take it on both sides. So 10 power on the LHS, you have minus alpha into L divided by 10. 10 power minus alpha into L by 10 is equal to 10 power log to the base 10 P output by P input. This goes off, they both are inverse function. So you have P output by P input, okay, is equal to 10 to the power minus alpha into L divided by 10. Okay. Now you have the ratio. Now you don't have to worry about P output, P input, it's not given, fair enough. You have to just calculate only the ratio for different values of L and the fixed value of alpha. Alpha is known, L is known, alpha is 4.3 dB per kilometer. L can be split into two distances, 2/4 kilometer and 6/3/4 kilometer. So you can calculate. The first case, for case 1, for a station which is generating power and sending the signal, and when the signal is traveling 2/4 kilometer, what is the value of so-called your value of your P output by P input? Okay, so substitute the value of alpha and you get P output by P input for the distance of 2/4 kilometer is equal to 10 power minus 4.3 into 2.25 divided by 10. Okay, 2.25 is 2/4. Okay, quarter of a kilometer is 0.25 meter. Okay, 0.25 kilometer. Okay, all right. Now 250 meter is 0.25 kilometer. So you have the value P out by P input after 2/4 kilometer is 0.1077. Okay. You found out the ratio. Now you compare when you increase the so-called your distance, what would this alpha be? Will it reduce or increase? Obviously it has to decrease, the alpha has to decrease, and you see for the case of 3 times the value of 2/4 kilometer, which is 6/3/4, which is 6.75 kilometer, make it as a so called your decimal values, so it will be easy. Substituting the values of alpha, we get P output by P input for 6/4 kilometer, that is 6/3/4 kilometer, which is 3 times the distance of this. So it is 10 power minus 4.3, which is alpha, into 6.75 by 10, which is equal to 0.001252, which is quite obvious. We can already expect that more the length, you have more the so-called the losses. Therefore, alpha will be directly proportional to the intensity of this. So output intensity will of course be less. So output intensity of that is your power will be equal to this times the input intensity or the power. Okay, if you want to calculate the P output, it's just this times input intensity. Okay. This fraction of the initial intensity remains after 2 quarters and 3 times the distance is already calculated. Summarize it. Summary is the fraction of P output by P input after 2 quarter kilometer is 0.1077, and after 6 quarter kilometer or 634 kilometer is 0.00125. Okay. So this is very well understood when a signal is transmitted from, let's say, a BSNL office, okay, which is using optical fiber. And if you want to understand, okay, there are n number of so-called your losses that is happening. Okay, loss due to absorption, loss due to macroscopic bending, okay, scattering. All these are quantified using this your alpha. Alpha is the coefficient of attenuation. It will tell you for what distance and what nature of optical fiber the loss can be experienced. So whatever you put in P input, okay, at the output how much it will remain depending on the nature of this so-called loss is this much amount. If you put 100, okay, that input, so this output would be 100 times 0.1077. For the larger length, 100 times 0.0012. Obviously length increases, so you have more loss. Alright, this completes the assignment problems. Expect more assignments and video lectures, and happy learning. Thank you.